Hello and welcome to our Logism Circuit Simulator series. My name is Carlo Castillo from CPE107 Lab, Section B1, Group 4. And today I'm going to discuss to you the comparator circuit. So the comparator circuit is built upon the premise that we compare the two inputs to each other and we produce an output whether if it is A is greater than B, A is equal to B, or A is less than C. So with that idea, we can fill out the truth table for those cases. So for the case of A is greater than B, uh, the only case that this is true is where A is 1 and B is 0. So we put a 1 value right here and the rest will be 0. And for the case of A is equal to B, there are two cases for that. So where both A and B are 0 and both A and B are 1. So we place a true value right here and the rest will be 0. For the case of A is less than B, the only case where that is true is where A is 0 and B is 1. So we place a true value there and the remaining will be 0. And now we apply the sum of products to convert this into an equation. So we just convert the inputs for this one in the column A greater than B. Convert this one into literal, so that is A, B prime. And for the second column where A is equal to B, since there are two inputs, we will have two combination of literals. So we have the plus operation or the OR operation, and we convert the inputs 0, 0 and 1, 0. So as you can see, 0, 0 is the A prime, B prime, and the 1, 1 is the A, B. And as you can see, this equation right here exhibits the XOR operation. So if we look at the truth table of this equation, so let's say 0, 0, so 0 and 0, that is 0, 0 prime and 0 prime, which is 1, or them together, the output is 1, and 0 and 1, 0 and 1 is 0, 0 prime and 1 prime is 0, or them together, the output is 0. So as you can see, if we check them individually, this will be the case, and therefore we can convert this equation into an A XOR B. And then we can now use these three formulas to create a logism counterpart. So as you can see right here, we just use IC for NOT and excuse me, XOR and have a three output values. And if we look at the truth table of this circuit, it holds true. So as you can see, A equals B is 0, 0 and 1, 1. A is greater than B, that is for 1, 0, and A is less than B, that is for the case of 0, 1. So this is actually the same as the truth table before. But the problem arises is what if we need what if we want to compare more than one bit? So we now create a cascadable 1-bit comparator. So in the case where we want to compare more than 1 bit, so let's say 16-bit or 32-bit, we just cascade this 1-bit comparator to each other until we reach the desired amount of bits to compare. So I created a K-map for that. So this is the main uh, idea right here. So you have an additional input of C, D, E, and this C, D, E is actually the result of the comparison of the previous comparator. So for the I created a combination of 1, 0, 0 if the previous comparison resulted an equal uh, comparison. So I created a 0, 1, 0 for the greater and 0, 0, 1 for the less than. So as you can see, it is color coded, so it is easier to follow. And since the first one will have no inputs, the very first 1-bit comparator will have no inputs, so we also consider that combination, which is the 0, 0, 0. So, and now we look at the K-map for the equal, for the case of equality. So, as you can see right here, every column is color-coded, and the red ones are actually the do not care, or the where this combination does not actually happen, because in the logic of comparator, only one we only have one true value for the output. So in the case of 0, 1, 1, 1, 1, 0, 1, 1, 1, and 1, 0, 1, this is not going to happen to our circuit, because they have more than one in output that is true. So in the case of equal, again, we consider the black part, the gray part, that is for the no input. So meaning we we want we want to provide a true value for the case where there is no input from the previous comparator, and the case is actually equal. So we put a true value for the uh, combination 0, 0, 0, 0, 0, that is 5 zeros, and the combination of 1, 1, and 3 zeros. So as you can see, 0, 0 is equal and 1, 1 is equal. So that actually falls to our equality. And for the values of fuchsia, that is for the less. So meaning this is a came up for equal sign. So meaning if the input is if the input if the result of the previous comparator is actually less than, then this will not the output will be 0. So the same for the greater than, which is the sky blue right here. The output for the case of greater than is 0, because it is not equal. And then for the lime green right here, or the green, where the input from the output from the previous comparator states that the previous one is equal, then we proceed to our logic, that that then we look at the both of the inputs, and for the case of 0, 0, and 1, 1, we provide a true value for the combination of 0, 0, 1, 0, 0, that is true value right there, and 1, 1, 1, 0, 0, and we put a true value right there. And for the remaining two, the output for that combination is 0. And now if we look at the if we derive the formula from the K-map following the K-map rules, so we look at the values, the input values where it changed. So if the value change, we then remove it, we cancel it, and we retain the remaining, converting the remainder to its literal. So as you can see, since we only AB is constant right here, and the only thing that changed is the CDE, we compare them, and we can see that D prime and E prime remains the same, remains 0 all out. And now we combine that to the uh, literal uh, literal form of 0, 0, which is A prime, B prime, D prime, and E prime. So that is for the black group right here. And looking at this group for the sky blue, as you can see, we did not really change the columns, so we just copy the D prime, E prime. But since the input for AB is changed, is different, so we just convert the 1, 1 into its literal form, which is A, B. And then we can factor out the D prime, E prime right here. And we we have this as the remaining operation inside the parentheses, and you can see that if we lay out the truth table for this expressions, it mimics the operation of an XNOR gate. So we simply convert this into an XNOR with this symbol. So our final equation for the case for the equality is D prime E prime and A prime XNOR uh, A XNOR B, which is seen right here. So that is for our equality. And for the case of greater than, so meaning A is greater than B, so we look at the case where the input from the previous comparator is 0, 0, 0, meaning there is no input from the previous comparator. The only case that A is greater than B is when A is 1 and B is 0. So we put a 1 value right here, and the rest of this gray part is 0. And for the case of the fuchsia, since this is a table for the greater sign, meaning the value for this will be false. And for the sky blue part, we can see that uh, it states that the previous comparator states that the the result of the previous comparator is true, because looking right here, the greater than, the 0, 1, 0, meaning the previous one is true. So meaning the rest of the combination is also true. The logic here is that if we compare the most significant bit of two words, then the result is greater than, automatically the rest of it, automatically A is greater than B, because it is the most significant, and if we discover that it is already greater from the start, then it is indeed A is greater than B. So here, in the case of equality, meaning the previous comparator said that the previous bits are equal, so we look at the inputs. So what is the case that A is greater than B? And that is the case for the 1, 0 again. So we put a 1 value right here. So, and the rest of here is 0. And now we look at our K-map. So to fully derive the equation, so the X can be used as a grouping. So in order to uh, create a more simplified or efficient circuit, so meaning it will take less ICs. So if looking at the group of black right here, so these two, the third column and the fourth column are grouped together. So looking at that, so looking at the inputs for A and B, we can see that A and B change. So we just cancel A and B, and we look at the CDE. So right here, this is the black part. 0, 1, 1, that is for column 3, and 0, 1, 0 for the column 4. We compare them, and we can see that E changed from 1 to 0. So we cancel that out. And what remains is the C prime D. So that is for our black group, the C prime D. And the remaining sky blue group right here, we just since it is similar to the previous one, so 0, 0, 0, compare the 0, 0 and the 1, 0, 0, we can see that D prime and E prime remain, so that there's that. And then since A, B did not change, we just combine it together. So A, B prime, that is 1, 0, and D prime, E prime, that is for this part. So that is for our greater than uh, operation. And now we look at the less than operation. So this is the table came up for the less than. So again, looking if the input from the previous comparator is none, meaning there is no input from the previous comparator, we now look at the case where A and B is where we now look at the case where A is less than B. So the case for that is only 0, 1. So we put a true value there, and the remaining 3 is 0. And now we look at the 001, the colored fuchsia. So meaning this is for the less than uh, operation. So with this column states that the previous comparator said that the previous bits are actually less than less than. So meaning A is already less than B from the previous comparator. So we now have a value of true here. So that follows the same rule of the greater. So meaning if the most significant bit already said that A is less than B, then automatically it the rest will follow through, because from the very start, from the very most significant bit, we already proved that it is true that A is less than B. So we have the one values right here. And for the case of the sky blue right here, the 010, that is the case for greater. But since this A came up for the greater operation, we place a 0 value. And then for the last part, so meaning the previous comparator said that both inputs of A and B are the same. So now we look at the case where A and B is we now look at the case where A is less than B for this circuit. So we can now see that the only case where it is true is when A is 0 and B is 0. So we put a true value right there, and the rest will be 0. And so now look at the K map right here. So again, we group the X that do not care in order to further simplify our uh, equation. So as you can see, A and B for the black group, A and B changed. So we cancel A and B, and we look at the CDE, which is 001 and 011. As you can see right here, the black part, we can see that the only input that changed is D. So from 0 to 1. So we cancel D, and what remains is the C prime and E. And now for the sky blue group, uh, we have two ones right here. So at the column of 01. So since AB did not change, we convert it into literals, A prime B. And we look at the comparison of the columns, which is 00100. We can see that C changed from 0 to 1. So it is cancelled out. And then we get the remaining, which is the D prime E prime. So this is the equation for the case for the less operation. And now we just combine this into we just convert this into a circuit, logism circuit. So looking at right here, this is the logism counterpart of these three formulas right here. So this is the logism counterpart. So as you can see, I use the NOT gate, XNOR gate, AND gate. I use three AND ICs, one OR IC, one XNOR, and one NOT. So I made a label since I have more time to so that I won't confuse myself. So let's see if in the case where CDE doesn't have input, so it is 0. We light up A. As you can see, it states that A is greater than B. If we light them together, both are 1. So it states that A is equals to B. And if we make it 0, 1, so it states that A is less than B. And if we turn them off altogether, then the output is equal. So as you can see right here, so if the input from the previous comparator is already greater than, then this input doesn't matter at all. So as you can see, if whatever combination for this, the output doesn't change because the previous one already stated that it is already greater than. So that is the same for the less than. So if we change A and B, as you can see, the output A is less than B, it doesn't change. But if we look at the case of equal right here, if we change the input of A and B, as you can see, it also changes because it states that the previous comparator said that the the other two bits, the previous two bits are equal. So we need to compare them again. So there. And since created this, so if we just I modify the circuit appearance in order to make it cascadable. So the three outputs are at the very top of the right side, and the three inputs from the previous comparator are from the lower left side. The three inputs right here. So looking at our 5-bit comparator, as you can see, uh, this one. So as you can see, uh, since I made it cascadable, we just combined the remaining the output of the previous comparator to the input of the next comparator with regards to the equalities. So we just connect the 5-digit input right here and then into its respective A and B lines. So as you can see, this is the null input where the case is 0, 0. Because yeah. And then if we actually change this one, so let's start from the easiest, smallest. So as you can see, if A is uh, 0, 0, 0, 0, 1 and B is 0, 0, 0, 0, the output is A is greater than B. And if we copy the input of A to B, we can see that A is equal to B because looking at the inputs right here, it is actually the same. And if we say 0, 1, 0, 0, 1 for input A, and for input B, we have 0, 0, 0, 1, 1, you can see that A is greater than B. So until we change the most significant digit, it will always be greater than. So as you can see, I'm changing the least significant. So the significant bit is being changed, but nothing is changing for the output. So as you can see, if now we change the most significant, we now have 4, 0, 0, 1, 1, 1, 1 for B, and A is 0, 1, 0, 0, 1. You can now see that A is less than B. So it is actually holds true. So there I'm creating more combinations. So as you can see, 1, 0, 0, 1, 1 is less than 1, 1, 1, 1, 1. So with this cascadable 1-bit comparator, we can now create a comparator for bits that are more than 1. And that's all for our Logician Circuit Simulator series. My name is Carlo Castillo from CPE107 Lab, Section B1, Group 4, and thank you for watching.